125% full load amps, or FLA, secondary protection for transformers is important for several reasons. Firstly, inrush current. When a transformer is energized, it experiences a surge of current known as inrush current. This surge can be significantly higher than the rated full load amps, sometimes up to 10 times higher. The 125% full load amps protection ensures that the secondary breaker or fuse can withstand this inrush current without tripping unnecessarily. Secondly, overloads. Transformers can be subjected to overloads due to increased load demands or system disturbances. The 125% full load amps protection provides a margin to accommodate temporary overloads, such as those experienced during motor starting, without causing the protection device to trip. Thirdly, aging and deterioration. Over time, transformers may degrade, leading to increased losses and reduced efficiency. The 125% full load amps protection compensates for this potential degradation, ensuring continued protection even as the transformer ages. Fourthly, safety margin. The additional 25% margin acts as a safety buffer to prevent nuisance tripping and ensures reliable operation under varying load conditions. Now, let's discuss the difference between breakers and fuses in this context. Circuit breakers are adjustable devices that can be set to trip at different current thresholds. Breakers used for transformer secondary protection typically have a high instantaneous trip setting to withstand inrush currents. They can also be equipped with time delay settings to prevent nuisance tripping during temporary overloads. Fuses, on the other hand, are one-time use devices that rupture to protect the circuit from overcurrents. They are rated for a specific current and cannot be adjusted. Fuses used for transformer secondary protection must be carefully selected to withstand inrush currents without blowing prematurely. The type of breaker or fuse used can indeed influence the secondary protection settings. Current limiting breakers limit the peak current during inrush, which reduces stress on the transformer. These breakers may allow for higher secondary protection settings because they effectively mitigate the impact of the inrush current. Expulsion fuses prevent current from flowing back into the transformer during a fault, which can help to prevent further damage. These fuses may require lower secondary protection settings to ensure that they operate quickly and effectively under fault conditions. In conclusion, 125% full load amp secondary protection for transformers is a common practice that is necessary to ensure reliable operation and to withstand inrush currents, overloads, and potential transformer deterioration. The appropriate protection settings and the choice between breakers and fuses depend on the specific transformer and the overall system requirements. To elaborate further on the specifics of choosing between circuit breakers and fuses, consider the following aspect. For circuit breakers, several types are commonly used for transformer protection. Molded case circuit breakers, or MCCBs, are widely applied and offer adjustable trip settings, allowing for fine-tuning of the protection characteristics. These breakers often include both instantaneous and time delay trip functions, providing flexibility in handling both short circuit and overload conditions. Insulated case circuit breakers, or ICBs, are typically used in high current applications and offer similar adjustable trip settings as MCCBs but with higher interrupting capacities. Solid-state trip units are commonly incorporated into both MCCBs and ICBs, providing advanced protection features such as ground fault protection, phase imbalance detection, and programmable trip curves. These features enhance the overall protection scheme and allow for more precise coordination with other protective devices in the system. When selecting a circuit breaker for transformer secondary protection, several factors must be considered. The continuous current rating of the breaker should be at least 125% of the transformer's full load amp secondary current to accommodate overloads and inrush currents. The interrupting capacity of the breaker must be sufficient to withstand the maximum fault current available at the transformer secondary terminals. Coordination with upstream and downstream protective devices is crucial to ensure selective tripping, minimizing the extent of any service interruption during a fault. The trip curve of the breaker should be carefully selected to provide adequate protection against overloads and short circuits while avoiding nuisance tripping due to inrush currents or temporary overloads. Now, let's consider fuses. Fuses are simple, reliable, and cost-effective overcurrent protection devices. They are available in various types, each with specific characteristics suited for different applications. Current-limiting fuses are designed to rapidly interrupt high fault currents, limiting the peak current and energy let through to the protected equipment. These fuses are particularly effective in protecting transformers from severe short circuits. Time delay fuses, also known as dual-element fuses, are designed to withstand temporary overloads, such as motor starting currents, without opening. They provide excellent protection against sustained overloads while avoiding nuisance tripping. Fast-acting fuses are designed to open quickly in response to overcurrents, providing rapid protection against short circuits. They are typically used in applications where sensitive electronic components need to be protected. When selecting fuses for transformer secondary protection, several factors should be taken into account. The amp rating of the fuse should be selected to provide adequate protection against overloads and short circuits while allowing for inrush currents. Time current characteristics, or TCC curves of the fuse should be carefully reviewed to ensure coordination with other protective devices in the system. The interrupting rating of the fuse must be sufficient to withstand the maximum fault current available at the transformer secondary terminals. The fuse type should be selected based on the specific application requirements, considering factors such as the severity of potential fault currents, the need for time delay, and the sensitivity of protected equipment. Furthermore, the specific type of transformer being protected can also influence the choice of protection method and settings. For example, dry-type transformers, which are commonly used in indoor applications, may have different thermal characteristics compared to oil-filled transformers used in outdoor substations. Dry-type transformers typically have lower thermal mass and may be more susceptible to overheating under overload conditions. Therefore, the protection scheme for dry-type transformers may need to be more sensitive and responsive to overload conditions. Oil-filled transformers, on the other hand, have higher thermal mass and can withstand overloads for longer durations without overheating. However, oil-filled transformers also present additional hazards such as the risk of oil spills and fires. The protection scheme for oil-filled transformers should include features such as oil temperature monitoring and gas accumulation detection to provide early warning of potential problems. In addition to overcurrent protection, transformers may also require other types of protection, such as differential protection and sudden pressure relays. Differential protection is a sophisticated protection scheme that compares the current entering and leaving the transformer. Any significant difference between these currents indicates an internal fault within the transformer, and the differential relay will trip to isolate the transformer from the system. Sudden pressure relays are designed to detect rapid increases in pressure within the transformer tank, which can indicate a severe internal fault. These relays provide fast and reliable protection against catastrophic transformer failures. The National Electrical Code, or NEC, provides specific guidelines for transformer protection, including requirements for overcurrent protection, grounding, and disconnecting means. Section 450.3 of the NEC covers transformer overcurrent protection and specifies the maximum allowable overcurrent protection device rating or setting based on the transformer's rated primary and secondary currents. It is critical to adhere to these guidelines to ensure safe and reliable operation of transformers. When applying the NEC requirements, it's important to consider the specific characteristics of the transformer and the connected load. For example, if the transformer is supplying a motor load, the overcurrent protection device must be sized to accommodate the motor's starting current, which can be several times higher than its full load running current. The NEC also provides guidelines for transformer grounding, which is essential for personnel safety and equipment protection. Proper grounding helps to limit the voltage rise during a fault and provides a low impedance path for fault current to flow back to the source, allowing protective devices to quickly clear the fault. In addition to the NEC, other industry standards and guidelines may also be relevant to transformer protection. The Institute of Electrical and Electronics Engineers, or IEE, provides various standards related to transformer protection, including standards for relay settings, coordination, and testing. These standards offer valuable guidance for designing and implementing effective transformer protection schemes. When designing a transformer protection scheme, it's important to consider the overall system configuration and coordination with other protective devices. Coordination studies should be performed to ensure that protective devices are properly coordinated to minimize the extent of any service interruption during a fault. These studies involve analyzing the time current characteristics of all protective devices in the system to ensure that the device closest to the fault will operate first, isolating the faulted section while leaving the rest of the system unaffected. Proper coordination requires careful selection of device settings and consideration of factors such as fault current levels, operating times, and device interrupting capacities. Furthermore, regular testing and maintenance of transformer protection systems are essential to ensure their continued reliability. Protective relays and circuit breakers should be periodically tested to verify their proper operation and calibration. Fuses should be inspected for damage or deterioration and replaced as needed. Insulation resistance testing, or mega testing, should be performed on transformer windings to assess the condition of the insulation. Oil samples should be taken from oil-filled transformers and analyzed for contaminants and other indicators of potential problems. Regular maintenance and testing help to identify and address potential problems before they can lead to equipment failures or safety hazards. In summary, selecting the appropriate overcurrent protection for a transformer involves a comprehensive understanding of transformer characteristics, system requirements, and applicable codes and standards. Factors such as inrush current, overload capacity, fault current levels, and coordination with other protective devices must be carefully considered. Regular testing and maintenance are essential to ensure the continued reliability and effectiveness of the protection system. When designing a transformer protection scheme, it's important to involve qualified electrical engineers and technicians who have experience in transformer protection and coordination. These professionals can provide valuable expertise and guidance to ensure that the protection system is properly designed, installed, and maintained. Remember that transformer protection is a critical aspect of electrical system safety and reliability. By following best practices and adhering to applicable codes and standards, you can help to ensure the safe and reliable operation of transformers and the electrical systems they serve. In addition to the technical considerations, there are also economic factors to consider when selecting transformer protection. The cost of the protection equipment itself, as well as the cost of installation, testing, and maintenance, should be weighed against the potential costs associated with transformer failures such as downtime, equipment replacement, and lost revenue. In some cases, it may be cost-effective to invest in more sophisticated protection schemes that provide enhanced reliability and reduce the risk of costly failures. For example, differential protection can be more expensive than simple overcurrent protection, but it can provide more comprehensive protection against internal transformer faults, which can be very costly to repair. Similarly, using current-limiting fuses or breakers can reduce the stress on the transformer during fault conditions, extending its lifespan and reducing the risk of premature failure. The economic analysis should also consider the potential impact of downtime on the overall operation of the facility. If the transformer is supplying a critical load, such as a hospital or a data center, even a short interruption can have significant consequences. In these cases, it may be justified to invest in redundant transformer systems or backup power supplies to minimize the risk of downtime. Another important consideration is the environmental impact of transformer failures. Oil-filled transformers can release oil into the environment if they fail, which can cause soil and water contamination. Dry-type transformers do not have this risk, but they may be more susceptible to overheating and fire. The environmental impact of a transformer failure should be considered when selecting the type of transformer and the protection scheme. In some cases, it may be necessary to implement additional environmental protection measures, such as oil containment systems or fire suppression systems, to mitigate the potential environmental impact of a transformer failure. The selection of transformer protection should also take into account the potential for future changes in the electrical system. As loads are added or removed, the transformer's operating conditions may change, and the protection scheme may need to be adjusted accordingly. It's important to select protection devices that are flexible and adaptable to changing conditions. For example, circuit breakers with adjustable trip settings can be easily adjusted to accommodate changes in load current. Similarly, solid-state relays can be reprogrammed to provide different protection functions as needed. The long-term reliability of the protection equipment should also be considered. Protection devices should be selected based on their proven track record and their ability to withstand the harsh operating conditions typically found in electrical substations. Factors such as temperature, humidity, and vibration can affect the performance and lifespan of protection equipment. It's important to select devices that are designed to withstand these conditions and to perform regular maintenance to ensure their continued reliability. In addition to the technical and economic considerations, it's also important to consider the regulatory requirements that may apply to transformer protection. The NEC and other applicable codes and standards specify minimum requirements for transformer protection, and these requirements must be met to ensure compliance. It's important to stay up to date on the latest regulatory requirements and to ensure that the transformer protection scheme complies with all applicable codes and standards. The design and implementation of a transformer protection scheme should be a collaborative effort involving qualified electrical engineers, technicians, and other stakeholders. All stakeholders should be involved in the decision-making process to ensure that the protection scheme meets the needs of the facility and complies with all applicable requirements. Regular training should be provided to personnel who are responsible for operating and maintaining the transformer protection system. Training should cover the principles of transformer protection, the operation of the protection equipment, and the procedures for testing and maintaining the system. Personnel should be trained to recognize potential problems and to take corrective action as needed. Finally, it's important to document the transformer protection scheme and to keep the documentation up to date. The documentation should include detailed drawings of the protection system, equipment specifications, relay settings, coordination studies, and maintenance procedures. The documentation should be readily available to personnel who are responsible for operating and maintaining the system. By following these guidelines, you can ensure that your transformer protection scheme is effective, reliable, and compliant with all applicable requirements. This will help to protect your equipment, your personnel, and the environment.